Today we will discuss probability, we will discuss random experiments, counting rules, basic requirements for assigning probabilities, events, and how to calculate probability of an event. Some basic relationships of probability, like union of two events, intersection of two events, mutually exclusive events, complement of an event. We will also discuss independent events, conditional probability, and Bayes' theorem. So managers often base their decisions on an analysis of uncertainties. For example, what are the chances that sales will decrease if we increase prices? If we know for sure that the sales will increase if we increase prices, then we will do it, but we don't know for sure. We may increase the prices, sales will decrease or will increase, so there is an uncertainty. But still, we need to decide. We need to decide whether we will increase the prices or not. Or what is the likelihood a new assembly method will increase productivity? So you need to spend some money to apply the new assembly method. But if you know for sure that new assembly method will increase productivity, you would do it. But there is an uncertainty. But still you need to decide whether to implement a new assembly method or not. And there are many examples like this. We still have to do something, even though we have uncertainties, we still have to do something. So most of the decisions based on an analysis of uncertainties. So probability is a numerical measure of the likelihood that an event will occur, and always assigned on a scale from 0 to 1. So probability cannot be less than 0. Probability cannot be larger than 1. It is always between 0 and 1. If it is 0, this indicates an event is impossible to occur. If it is 1, this means it is certain to occur. So probability near 0 indicates an event is quite unlikely to occur. Probability near 1 indicates an event is almost certain to occur. So then, closer to 1, the likelihood of occurrence increases, and closer to 0, the likelihood of occurrence decreases. So what is a statistical experiment? When we say experiment in statistics, it is different than the experiment in physical sciences. In statistical experiments, probability determines outcomes. So then, once we say experiments in statistics, experiment is any event that generates well-defined outcomes. And even though it is repeated in exactly the same way, an entirely different outcome may occur. That's why they are also called random experiments. For example, rolling a die is considered an experiment. It generates well-defined outcomes, and even though it is repeated in exactly the same way, an entirely different outcome may occur. So you roll it 1, you get 6, you roll it again, you get 3. That's called random experiments. So experiment is a process that generates well-defined outcomes. And even though it is repeated in exactly the same way, an entirely different outcome may occur. What is a sample space? Sample space for an experiment is the set of all experimental outcomes, usually denoted by S. For example, if you roll a die, sample space is 1, 2, 3, 4, 5, 6. It's either exactly 1, exactly 2, exactly 3, 4, 5, 6. Cannot be anything else. An experimental outcome is also called a sample point. These are also called sample points or experimental outcomes. In the sample space, you have to list all possible outcomes for that experiment. For example, if you toss a coin, the sample space is head-tail. It's either head or tail. So just inspect the part, either defective or non-defective, conforming, non-conforming. If you conduct a sales call, may end up with purchase or no purchase. So these are the only two possible outcomes for that experiment. So in the statistics, the experiment is any process that generates well-defined outcomes, different than the physical sciences, such as roll a die 1 through 6. Play a football game, either win, lose, tie. You need to list all possible outcomes for that experiment, which is a sample space. Now we will look at this example. Bradley has invested in 2 stocks, Markle Oil and Collins Mining. Bradley has determined that the possible outcomes of these investments 3 months from now are as follows. So you can gain 10,000 from Markle Oil, can gain 5,000 from Markle Oil, or even can't gain or lose anything from Markle Oil, or he can lose $20,000 from Markle Oil. And Collins Mining, he can gain 8,000 or lose 2,000 from Collins Mining. Now we will discuss counting rules. We will discuss 3 counting rules here. We will discuss counting rule for multiple step experiments. We will discuss combination and the permutation. So why do we discuss the counting rules? Because being able to identify and count the experimental outcomes is a necessary step in assigning probabilities. What is the counting rule for multiple step experiment? If your experiment consists of k steps, so you have n1 possible outcomes for the first step, n2 possible outcomes for the second step, and nk possible outcomes for the k step, then the total number of experimental outcomes for this experiment is n1 times n2 times nk. For example, if we toss 2 coins, then how many total experimental outcomes do we have? We are tossing the 2 coins, so we can consider this as a 2-step experiment. Tossing the first coin is 1 step, the other coin is the second step. So we have 2 possible outcomes for the first coin and 2 for the second. So total 4 possible outcomes. To see this, we can also draw the tree diagram. So the tree diagram helps us to see the outcomes for multiple step experiment. It's the graphical representation of the multiple step experiment. So then we have 2 outcomes for the first, head, tail, head, tail, for the second, so then what are those outcomes? You can get head from first one, head from the second. You can get head from first, tail from second, tail from first, head from second, and tail, tail. So this is the tree diagram for if you toss the 2 coins. So we have 4 outcomes. What are those outcomes? Head, 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 tail, tail, head, tail, tail. But the good thing about the counting rule for multiple step experiment, it makes it possible to determine number of outcomes without listing them or without doing the tree diagram. So we can use this counting rule for multiple step experiments to determine the number of outcomes without drawing the tree diagram or the listing the outcomes. That's the good thing about the counting rules. And being able to identify and count the experimental outcomes is a necessary step in assigning probabilities. So this is for multiple step experiments. How about the Bradley investment? Like we discussed here, Bradley is invested in 2 stocks, Mark Lloyd and Collins Mining. Now how many total experimental outcomes do we have from this investment? At the first time it may appear to be like we have 6 outcomes, but it's not the case because we are investing in those 2 stocks at the same time. So then you have 4 possible outcomes from Mark Lloyd and 2 possible outcomes from the Collins. So then this can be considered as 2-step experiments. You have 4 from Mark Lloyd and 2 from Collins, which is 8 outcomes. Total 8 outcomes from this investment. And to see this, we can look at the tree diagram for this example. So you can gain 10 from Mark Lloyd, 5 from Mark Lloyd, gain $5,000 from Mark Lloyd, or lose 20,000 from Mark Lloyd. But Collins, you have 2 options. You either gain 8,000 or lose 2,000. So gain 8, lose 2, gain 8, 2. So total we have 8 outcomes. What are those outcomes? 10, 8. What does this mean? You are gaining 10 from Mark Lloyd and gaining 8,000 from Collins Mining. So total gain from this investment, if this happens, then it is $18,000. Or you gain 10 from Mark Lloyd, lose 2 from Collins. So if this happens, you gain 10,000 from Mark Lloyd and lose 2,000 from Collins Mining, then total you are still gaining $8,000. Even though you are losing 2 from Collins, you are still, total gain from this investment will be $8,000. Or you gain 5 from Mark Lloyd, gain 8 from Collins, 5, 8. First number belongs to Mark Lloyd, second belongs to Collins Mining. If this happens, then you are gaining $13,000 from this investment, or you are gaining 5 from Mark Lloyd, lose 2 from Collins Mining, which is 5, negative 2. This means gain 5 from Mark Lloyd, lose 2 from Collins. And if this happens, then you're still gaining 3,000 total from the investment, or 0, 8. What does this mean? Even you're not gaining or losing anything from Mark Lloyd, but you are gaining 8 from Collins. If this happens, then you are gaining $8,000 from the investment, 0, negative 2. You are not gaining anything from Mark Lloyd, but you are losing 2 from Collins. And then from investment, you're losing $2,000. Or lose 20, gain 8. And if this happens, you are losing 20,000 from Mark Lloyd and gaining 8,000 from Collins. If this happens, then in total you are losing $12,000. Or you lose 20 from Mark Lloyd, lose $2,000 from Collins, negative 20, negative 2, then if this happens you are losing $22,000. from the investment. So as you see, we have 8 outcomes. So if you look at here, it may appear to be like we have 6 outcomes, but Bradley has invested in 2 stocks at the same time, so you can gain. So this is also can be considered as multiple step experiments. Investing Mark Lee's may consider as the first step. Investing Collins mining may be considered as the second step. So the total number of outcomes is 4 times 2. It's not 4 plus 2. It's 8 outcomes. And you can see that we have 8 outcomes here from this investment. Now the combination and the permutation. Now the combination, assume you are selecting 2 objects from set of 5 objects without replacement. Then how many different ways can you select 2 objects from 5 objects? Or for example, for a certain organization, you are selecting such as 2 students to represent the faculty or to represent the college. How many different ways can you select, for example, 2 students from maybe 100 students? Combination helps us to count, enables us to count the number of outcomes when n objects are to be selected from set of n objects, which is combination n choose n. So this is not divided by n. For example, 5, 2. Then how do we calculate this one? So this is not 5 divided by 2. So this is 5 factorial divided by 2 factorial times 5 minus 2 factorial. And so this, so you know what 5 factorial is? 5 factorial is 5 times 4 times 3 times 2 times 1. This is 5 factorial. But here in the denominator we have 5 minus 2 factorial, which is 3 factorial. So we can write this as 5 times 4. This is what? 3 factorial. So 5 times 4 times 3 factorial. Because we know we have 3 factorial in the denominator, so we can cancel the which is 10. 20 divided by 2. 2 factorial is 2, because 2 times 1, 2. 0 factorial is 1. By definition, 0 factorial is 1. Or if you have your calculator, you can use this NCR. 5, choose 2, which is 10. Now there are different applications of the permutation, but you can use the permutation to count the number of experimental outcomes when n objects are to be selected from a set of n objects, like the combination. But the difference is now the order of selection is important. So which one you select first and which one you select, the order of the selection now is important. And for example, if we have permutation, then it will be 5 factorial divided by 5 minus 2 factorial. 5 times 4 times 3 factorial, which is 20. To see the difference between combination and the permutation, we will look at this example. Consider a quality control procedure. So randomly select to test for defects. Now, how many combinations of two parts can be selected? Now, how many permutations? Now we will calculate the number of combinations and number of permutations. Like we did before. Number of combinations, which is 5 factorial divided by 2 factorial, 5 minus 2 factorial, which is 10. And the permutation, 5 factorial divided by 5 minus 2 factorial, which is 20. For permutations, so you can use NPR, so 5, NPR 2, which is 20. Now assume those parts are labeled as A. We have 5 parts, A, B, C, D, E. So we have 10 different ways to select 2 parts out of 5. Order doesn't matter. Then what are those outcomes? Then we can have AB, we can select AB, AC, AD, AE, BC, BD, BE, CD, CE, DE. 10 different ways to select 2 parts out of 5. Order doesn't matter. How about the number of permutations, which is 20? Again, we label A, B, C, D, E. So what are those outcomes? Now order matters. So if we have AB, then we have BA, AC, CA, AD, DA, AE, EA, BC, CD, CD, DC, PED. So now the permutation, selection of order matters, combination order doesn't matter. Now we will discuss basic requirements for assigning probabilities. How do you assign a probability to an outcome? First of all, probability can never be less than 0, it can never be larger than 1. So it has to be between 0 and 1 inclusively. And sum of the probabilities for all experimental outcomes must equal 1. Such as football game, outcomes win, lose, tie. So I cannot assign a probability of 1.02 to one outcome. It has to be between 0 and 1. So now, if this is 0.5, 0.3, so we only have 3 outcomes, win, lose, tie. If this is 0.5, probability of winning 0.5, probability of losing 0.2, then this probability can be 0.2, which sum must be 1. Cannot be less than 1, cannot be larger than 1. Sum of the probabilities for all experimental outcomes must equal 1. And these are the ways to assign probabilities. Classical method. If you have equally likely outcomes, then you use this method, which means probability of the occurrence of all outcomes are equal. So if you have equally likely outcomes, then you use classical method. You may not have equally likely outcomes. You may have some data, past data or historical data. You can use this data to assign probabilities. You can use relative frequency method to assign the probabilities. Or you may be expert in one area, such as in football. You may be expert and using your judgment, you can use some historic data and your judgment to assign these probabilities. So in this case, the assigning probabilities based on the judgment. Such as the rolling a die. So if an experiment has n possible outcomes, and they all equal likely outcomes, then each outcome has probability of 1 over n. Because the sum of the probabilities for all outcomes must be 1, and if you have n equally likely outcomes, then each outcome has probability of 1 over n. Like rolling a die. You have 6 outcomes, each has probability of 1 over 6. Or tossing a coin. You have 2 outcomes, 2 equally likely outcomes, each has probability of 1 over 2. Sometimes we may not have equally likely outcomes. For example, Lucas tool rental would like to assign probabilities to the number of car polishers it rents each day. Office records show the following frequencies of daily rentals for the last 40 days. Now, based on this, it seems like renting such as 2 polisher in any given day is more likely than renting 4 polishers, because 18 out of 40 days they rented 2 polishers, only 2 out of 40 days they rented 4 polishers. So it seems like we don't have equally likely outcomes. It seems like renting 2 polishers is more likely than renting 4 polishers. In this case, you can either use the subjective method or you can use the relative frequency method. How do we use the relative frequency method? We calculate the relative frequencies and we use relative frequencies as the probabilities to assign probabilities. How do we calculate relative frequencies? Total 40 days. So 4 out of 40 days they couldn't rent any polisher 4 out of 40 days. So then this will be 0.1. 6 out of 40 days they rented 1 polisher. 18 out of 40 days they rented 2 polishers. 10 out of 40 days they rented 3 polishers, and 2 out of 40 days they rented 4 polishers. And sum must be 1, which is sum of the probabilities for all outcomes must be 1. So what's the probability of renting 4 polishers in any given day? Based on the relative frequency method, it is 0.05. What's the probability of renting 3 polishers in any given day? 0.25. This is the relative frequency method. You use the relative frequencies, calculate the relative frequencies, and they are the probabilities. Frequency divided by total number of days. You can also use subjective method. Now sometimes you may not assign probabilities based on the historical data only. Like here we use the historical data and assign the probabilities based on this data. But sometimes it may not work. You may combine the data, your experience, your intuition, combine it with the data. You can use the data, but as well as your experience and your intuition. So that ultimately a probability value should express our degree of belief that the experimental outcome will occur. Such as here, how did we calculate these probabilities? They're estimates. So analysts made the following estimates. We didn't calculate them. Somebody expert in that area made those estimates. Of course, the sum must be 1, and you cannot assign probability larger than 1 to any outcome or less than 1. And the sum of the probabilities must be 1. So an analyst made the following estimates. A different analyst may make different estimates We didn't calculate those. These are the estimates based on the subjective method. Now we will discuss the events and how to calculate the probability of an event. What is an event? Which is a collection of sample points. And how do we calculate the probability of an event? Which is equal to the, if we know the sample points in the event, and if we can assign the probabilities to each sample point in the event, we can easily calculate the probability of an event, which is the sum of the probabilities of the sample points in the event. But sometimes we may not be able to assign the probabilities to each outcome, but if we can identify all the sample points of an experiment and assign a probability to each, we can easily calculate the probability of an event by summing the probabilities of the sample point in the event. For example, this Bradley investment. Let's define one event, M. Markle oil profitable. Now these are the sample points, experimental outcomes for this experiment. Now this is one event, Markle oil profitable. Now we look at these outcomes. Which one's Markle oil is profitable? Remember, the first one belongs to Markle oil, second one belongs to Collins Mining. So if we look at this one, now this one, Markle is profitable because you are gaining 10,000 from Markle. Now since this event says Markle oil profitable, we look at the ones that Markle is profitable. 10 negative 2, Markle is profitable. 5 8, Markle is profitable. 5 negative 2, you are losing 2,000 from Collins, but Markle is still profitable. How about 0 8? No, because Markle is not profitable. It is even. Not profitable. You are losing 20,000 from Markle, still it's not profitable. So this event specifically says Markle oil profitable. So we have these 4 outcomes in this event, which means 10 8, 10 negative 2, 5 8, 5 negative 2. Now how do we calculate the probability of n? We add the probabilities of the outcomes. Ten 8. What's the probability of this outcome? 0.2. 10 negative 2, 0.08. 5 8, 0.16. 5 negative 2, 0.26. So then what's the probability of this outcome? 0.7. You can define another event. Say C, Collins Mining profitable. Now, which outcomes will be in that C, which is in this event, Collins Mining profitable? This one, Collins is profitable. are gaining 8,000 from Collins Mining. How about this one? 10 negative 2. You are losing 2,000 from Collins Mining. So Collins is not profitable. Collins is profitable. You are gaining 8,000 from Collins. So first one belongs to Markle Oil, second belongs to Collins Mining. 08, Collins is profitable. You are gaining $8,000 from Collins Mining. 0 negative 2, no. Negative 20, negative 28. Collins is profitable. Even though you are losing net $12,000, still this will be in this event because this event says Collins is profitable. And here Collins is profitable. You are gaining $8,000 from Collins Mining. So now this will be 10.8. Five 8, 0 8, negative 28. So then how do we get the probability of C? We are summing the probabilities of the sample points in this event. So probability 10.8 plus probability 5.8 plus 0.8 negative 28. Probability of this outcome 0.2, 58.16. Probability of 0.8, 0.1, negative 28. This is 0.48. Probability of C. This is how we calculate the probability of an event. If we know the sample points in the event and we can assign the probabilities to the sample points, we can easily calculate the probability of an event. Markle Oil profitable. Collins Mining. You can define another event, say investment is profitable. Then you only look at the ones that investment is profitable. You can also calculate that event, probability of that event. But sometimes we may not know all the sample points in the event, and we may not assign the probabilities. In that case, we can use some basic relationships to calculate the probability of an event without knowledge of the sample point probabilities, such as complement of an event, union of two events, intersection of two events, and mutually exclusive events. What's the complement? Complement of an event. Complement of event is defined to be the event consisting of all sample points that are not in A, such as this is event A, so this is A. This is the Venn diagram, and A complement is all sample points that are not in A. This is A complement. A and A complement together gives a sample space. So then this means probability of an event plus probability of its complement is always 1 because it gives a sample space. Probability of sample space is 1. So probability of an event plus probability of its complement is always 1. So if you know the probability of event, you can easily calculate the probability of the complement by just subtracting that from 1. Subtracting the probability of event from 1. So this means that probability of A will be then 1 minus probability of A complement. So then you can calculate the probability of A if you know the A complement, probability of A complement. without knowing the sample point probabilities, or probability of A complement is 1 minus probability of A. Union of two events. Union of two events is the event containing all sample points that are in both, that are in A or B. Like A or B, which also includes the both. So union is denoted by A union B, which is this area in the Venn diagram, A or B. This is the union. Such as for this example, how do we calculate M union C? What does this mean? At least one of them is profitable. Either markedly profitable or Collins profitable, or the both. Which ones should be in M union C? We look at the outcomes. 10, 8, they're both profitable, so this should be here. 10, negative 2, markedly profitable should be here. 5, 8, both profitable should be here. 5, negative 2, markedly profitable should be here. 0, 8, Collins profitable, it should be here. Negative 20, 8, Collins profitable. This is M union C. And what's the probability of M union C? So you only exclude the ones that none of them is profitable, which is sum of these sample points. So then probability of M union C will be 0.2 plus 0.08, 16, 26, 0.82. M union C. Markedly profitable or Collins or both. So then this means at least one of them is profitable. What's the probability that at least one of the investment is profitable? Intersection of events. We only know here is a set of sample points that are in both A and B. So we only look at the ones that are in both A and B. Intersection. Union, sample points that are in either that are in A or B or both, and the intersection in both A and B. So how about if we look at this example, how about M intersects C? Which ones in M intersects C? That both profitable. 10, 8, both profitable. Both Markley and Collins profitable. 5, 8, both. No, Collins not profitable, Markley not profitable. So only these two. So then probability of M intersect C 10.8.2 plus 58.16, which is 0.36 intersection. So do you see the difference between the union and intersection? In the intersection, what's the probability that they both profitable, both Markley and Collins profitable? Only these two sample points, 10.8 and 5.8. Because if we look at here, Collins is not profitable. Here, Markley is not profitable. So we only include the ones that both profitable. But in the union, we include the ones that are both profitable, only Markley profitable, and only Collins profitable, which is the probability that at least one of them is profitable, M union C. And the addition law provides a way to calculate the union of two events. Or you can have addition law for 3 events, 4 events or more, but this is for 2 events. Union of events. So then which is probability of A plus probability of B minus A intersect B. Why do we have A intersect probability of A intersect B here? If we look at the Venn diagram, say this is A, this is B. So once we say probability of A, which is this area in the Venn diagram, which as you see includes intersection, already includes intersection, plus probability of B. So now you are including the intersection twice. So that's why you subtract one of them. So then it is A probability of A plus probability of B minus the probability of intersection. Why do we have minus intersection? Because we are including, once we say probability of A, already we are including the intersection plus B, we are including intersection twice. So we are subtracting the one of them. And we can calculate the probability of M union C using the addition law, which is probability of M plus probability of C minus M intersect C, which we get the same answer as M union C, like using the definition of an event, we get the same answer using the addition law. What is mutually exclusive events? Two events are mutually exclusive if they have no sample points in common. They cannot happen at the same time. If one occurs, the other cannot occur. If one event occurs, the other cannot occur, mutually exclusive. So no sample points in common. As you see from the Venn diagram, they don't intersect. So if two events are mutually exclusive, since they cannot happen at the same time, probability of A intersect B is 0 if they are mutually exclusive. Probability of A intersect B is 0 for mutually exclusive events. No, they don't have any common sample points. So then the addition law. So addition law is always probability of A union B is probability of A plus probability of B minus intersection. But for mutually exclusive events, this is 0. So then if A and B are mutually exclusive, we can simply write the A union B as probability of A plus probability of B, because the intersection is 0. Suppose that we have a sample space, so let's look at this example. Before we discuss the conditional probability, and event A, E1, E2, B, E3, E4, find probability of A, probability of C, and probability of B, and probability of C. Now what's probability of A? Since they all equal likely outcomes, we have 5 outcomes. Each outcome has probability of 1 over 5. So then probability of, since they are equal likely outcomes, probability of E1 equals E2 equals E3, E4. Each has probability of 1 over n, which is 1 over 5.2. So then probability of A is probability of E1 plus probability of E2, which is they both 0.2, so 0.4. Probability of B, E3 plus E4, 0.4. 0.6. Now find probability of A union B. Are A and B are A and B mutually exclusive? Now let's first draw the Venn diagram. To see this better. So we have A. Are there any common sample points between A and B? No common sample points, so they are mutually exclusive. How about A and C? Do they intersect? Yes, E2 is common. B and C, yes. So then it will be like this. C is like this. Now where will we put A, E1? E1 will be here. Where will we put E2? E2 is common between, so A has E2 and C has E2, so in the intersection. How about E3? B has E3 and C has E3 in the intersection of B and C. E4 only B and E5 only C. So this is the Venn diagram. How about probability of A union B? Which sample points do we have in A union B? E1, E2, E3, E4. They are mutually exclusive. They don't have any common sample points, so their probability will be 0.8. Since they are mutually exclusive, it is also, we can use addition law, which is probability of A plus probability of B minus the intersection. Probability of A is 0.4, B is 0.4. Intersection is 0, so then it is 0.8. Same. How about A complement, C complement? What is probability of A complement and probability of C complement? A complement, all sample points that are not in A. Which ones? E2, E3, E5. A complement, outside of A, all that are not in A. E3, E4, E5. And probability of A complement is 0.6. You either write the sample point probabilities or it is 1 minus probability of A, which is 0.6. C complement, all sample points that are not in C, this is C. Which ones are not in C? E1 and E4. So probability of C complement is 0.4. Find A union B complement. Probability of A union B complement. So then A union B complement. Which ones do we have in A? E1, E2. And which ones do we have in B complement? All sample points that are not in B, E1, E2, E5. So then in A union B complement, we have E1, E2, E5. So then probability of A union B complement is 0.6. Now what is probability of B union C? Sample points that are in B or C or both. We have E2, E3, E4 in B, E2, E3, E5. So which sample points do we have in B union C? E2, E3, E4, E5, which is 0.8. Now we will discuss the conditional probability. Now assume you have two related events, say A and B, with some initial probabilities, probability of A, probability of B. So if we know that if one of them has already occurred, we would like to use this information to calculate the probability of the other one. So if we know that such as B has already occurred, we would like to use this information, since if they are related events, if one of them occurs, we would like to use this information to calculate the probability of the other one. So conditional probability of A given B, A given B, probability of A given B. This means probability of A given B has already occurred. This is probability of A intersect B divided by probability of given B, B. So we have two events, related events, with some initial probabilities. If we know that one of them has already occurred, we would like to use this new information to calculate the probability of the other one. So this is probability of A given B. Conditional probability of A given B has already occurred, which is probability of A intersect B divided by probability of B. Same thing as like B given A. If they are related events and if we know that A has already occurred, we would like to use this new information to calculate the probability of B. This is the conditional probability of B given A has already occurred, which is probability of B intersect A divided by probability of A. But we know that A intersect, probability of A intersect B and B intersect A are same. This is the conditional probability. Such as Mark Oil and Collins Mining. If we know that Mark Oil is profitable, that event occurred, so event M has already occurred, then we would like to use this new information to calculate the probability of C. Collins Mining is profitable. So this is a conditional probability of C given M has already occurred, which is probability of C intersect M divided by probability of M, which is 0.5143. Or you can calculate probability of M given C. What's the probability of M? Probability that Mark Oil is profitable given Collins Mining is profitable, which is M intersect C divided by probability of C. Probability of C is 0.5143. for it. Ch05. So multiplication law, so addition law provides a way to calculate the union of two events. Multiplication law provides a way to calculate the intersection of two events. So if we know that A given B is probability of A intersect B divided by probability of B, and B given A, B intersect A divided by probability of A. So if we know A intersect B, if we know A given B and probability of B, how do you calculate this for A intersect B? We cross multiply it, which is A given B over probability of B. This is also B intersect A and A intersect B are the same, which is probability of B given A times probability of B, probability of A. So this provides a way to calculate the intersection of two events. Sometimes A intersect B may not given, but you may know A given B and probability of B. So you can calculate the A intersect B by multiplying those two. So assume C given M given, probability of M is given. Then how do you calculate M intersects C? You multiply those two. This is the joint probability table for this example. Joint probabilities appear in the body of the table and marginal probabilities appear in the margin. So now this is probability of M, which is markedly oil profitable. Now this is probability of M complement. If probability of M is 0.7, probability of M complement is 1 minus 0.7. And this is what? Probability of C. Collins mining is profitable. And this is probability of C complement, which is 1 minus probability of C, 0.52, which is Collins mining is not profitable. How about this one? MC. So this is probability of M intersects C. They both profitable. How about this one? This is probability of M intersects C complement. Markedly profitable, and Collins is not profitable. And this one, probability of M complement intersects C. Markedly is not profitable, and Collins is profitable. This is M complement intersects C complement. None of them is profitable. So we discussed the mutually exclusive events. Now we will discuss the independent events. What's an independent event? If the probability of event B is not altered or affected by knowing event A. So we know event A exists, but probability of B is not altered or affected by knowing event A exists. Then event A and B are independent. So if they are independent, what is A given B? Probability of A given B. What's probability of A given B has already occurred. But if they are independent, then given B has already occurred doesn't alter the probability of A. So this is still probability of A. Same thing for B given A. If they are independent, then given A has already occurred doesn't change the probability of B. So B given A still equals the probability of B. If two events are independent, A given B is probability of A, B given A is probability of B. Now how do we know whether, so then what happens to the multiplication law if two events are independent? A given B is A. So then A intersect B becomes probability of A times probability of B. So if two events are independent, A intersect B is always probability of A times probability of B. This is always the case. Now we can check, are events M and C independent? How do we determine this? Once we multiply probability of M times probability of C, if they are independent, this must equal to probability of M intersect C, which is 0.36. Is it equal to 0.36? 0.7 times 0.48, which is 0.34, is not equal to M intersect C, probability of M intersect C, which is 0.36. So then M and C are not independent. This is how we check the independence. So now it is important to know the difference between independent and mutually exclusive events. Mutually exclusive events, they don't have any common sample points. So their intersection is zero. They cannot happen at the same time. So two events with non-zero probabilities cannot be both mutually exclusive and independent. If two events are mutually exclusive, if one mutually exclusive event is known to occur, the other cannot occur. So then they are dependent. And two events that are not mutually exclusive might or might not be independent. So we can look into it like this. They don't have any common sample points, so then probability of A intersect B for mutually exclusive events is zero. But independent events, what is probability of A intersect B? Always probability of A times probability of B. So if they are independent, then A intersect B is not zero. It is probability of A times probability of B. How about A union B? So what is an example to mutually exclusive? You cannot both pass and fail the course. If you pass it, then you don't fail. That can't happen at the same time. A union B is then reduces the A plus B, probability of A plus probability of B, because it is always probability of A plus probability of B minus the probability of A intersect B. But probability of A intersect B is zero if they are mutually exclusive. So then A union B is just A plus probability of A probability of B. Minus the intersection. And this is how we calculate the intersection if they are independent. How about if two events are mutually exclusive? What is A given B if two events are mutually exclusive? What's the probability of A given B has already occurred? If B has already occurred, A cannot occur if they are mutually exclusive. So this is always zero. Or we know that this is A intersect B. since A intersect B is 0, 0 divided by anything is 0. Which makes sense, because if A and B are mutually exclusive, if B occurs, A cannot occur. So probability of A given B has already occurred is 0. How about if A and B are independent? What is A given B? If they are independent, given B has already occurred, doesn't change the probability of A. This is A. Same thing as B given A. 0. If they are independent, it's important to know the difference between mutually exclusive and independent events. We will discuss the Bayes theorem later. So far we discussed the events, we discussed counting rules, experiments, sample space, how to calculate the probability of an event, basic rules assigning the probabilities, some basic relationships like complement of an event, union of two events, intersection of events, two events, addition law, mutually exclusive events, independent events, the difference between mutually exclusive and independent events, discuss the conditional probability. So then later we will discuss the Bayes theorem.